created by the Big Bang. Yes? And so if somebody says, where did the Big Bang happen? You guys are now the experts, right? And so what you say, and they will think you're crazy, is you just say, the Big Bang happened right there. And they'll of course, all kind of back away from you, right? And then you say, it also happened in Kentucky. And New Jersey. And it happened in Andromeda. That's because, here's why, okay? It happened everywhere. Everywhere that is now was in the Big Bang because space itself unfolded from the Big Bang. Yes? This is weird. What caused it to go bang? They've actually looked at the primeval sound waves. The universe had when it expanded, and I'll show you this, right? And they think that they heard a word like oops right before the Big Bang. No, this is one of the fundamental dilemmas of the Big Bang, right? Is there paradoxes? That's what I'm looking for. The fundamental paradox of the Big Bang is we're pretty sure that it was a uncertainty, like a quantum fluctuation of something, but of what was it a quantum fluctuation, right? It's like Winnie the Pooh, right? Winnie the Pooh is outside Rabbit's rabbit hole, and he says, hello, is anybody in there? And Rabbit says, no, nobody's home. And Pooh reasons this out, right? Pooh says, there must be someone home to say that nobody's home, right? So the question is, if the Big Bang was a quantum fluctuation, this is one of these bedrock paradoxes, right? Of what was it a quantum fluctuation? I don't know. So you can insert your deity. Suffice it to say, there's sufficient place to, we're not going to eliminate all space for your deity. If you want a deity, put it there, or something like that, right? Because there's all sorts of interesting things, but that's not today. That's next time. Okay. So that's right. So okay, let's keep going. Okay. If it once was hot, it's now vastly expanded, right? And it should still be a little warm. We should see in the distance 13.7 or so billion light years away from us, because now distance is time, right? Yes? Okay. 13.7 billion light years from us, we should see the Big Bang. If we look, and where do we look to see the Big Bang? Everywhere. Away from us, because it's back in time. Away from us is back in time. I'm sorry if I'm hurting your brain, right? But it's expanded, right? It's a four-dimensional sphere, or some sort of shape, right, that has expanded. And so to see the Big Bang, we just have to look away from us, far, far away from us, and we have to look at the right frequency. So this is what Gamow says, is now, basically, if we look far, far away from us, we should see a big fiery wall. Only it's going to be an icy fiery wall, because that radiation has been stretched by the stretching of the universe, right? Okay, so they predict that you should see, and it should be the background radiation. This is called cosmic microwave background radiation, or from here on out, CMBR. Okay, you should see this fiery wall, and it was super energetic photons. Now it doesn't have so much energy. It's been stretched to the point where it's like really, really cold. Yeah? It's stretched to the point where it's got a Wien temperature of 5 kelvins. Now, what do we mean by Wien temperature? Well, that is this whole thing, right? That the wavelength is equal to 2.90 times 10 to the minus third. That's a really crazy 3. You try to talk and write numbers. Meters Kelvin over the temperature. If you put 2.736 or 5 kelvins or something on there, you'll get a wavelength like this. Okay? So he predicted that it should be about 5 kelvins, right? And it should display a blackbody curve. Now, what do we mean by this? Blackbody radiation is the radiation given off by warm objects. You guys are radiating blackbody radiation. The room is radiating energy to you. If the walls of the room, if we replaced them with ice-cold walls and kept the air temperature the same, you would feel noticeably colder. That's part of your comfort, is the warmth of the walls, because of this radiative equilibrium between you and the walls. You are radiating blackbody radiation. The walls are radiating somewhat less back to you, right? Okay. Humidity in the air also affects your comfort level, right? So a bonfire radiates blackbody radiation. That's what keeps you from walking right up to it. It's like, oh God, that's hot. Yeah. Okay. The air is still cold enough that you can see your breath in the air. Have you been at a bonfire when it's cold? Yeah. The air is cold. You're not getting heated by the air. It's this radiation coming from, right? The sun heats us with blackbody radiation. So it's the radiation of a hot object, and it's got a distinctive curve, doesn't it? Yeah. So if the Big Bang theory is correct, we ought to be able to test this by looking away from any star, carefully looking where there is not like Milky Way stars, into the distance. We should see a big fiery wall. We should see this uniformly warm blackbody curve type radiation, right? Okay, it should be the same in all directions because all directions are the same. They all emerged from the singularity, right? In 1940, though, nobody really paid any attention to these predictions because why?
World War II?
Yeah, we were getting ready to fight a war, so any resources that might have gone into actually testing these were going into building ships and airplanes, right? Yeah, okay. And the other problem was that the predictions were about microwave radiation, and nobody had a radio telescope, much less one that could receive microwave radiation, right? So they made these predictions, they couldn't be tested, and so it was like, okay, that's an interesting paper, good enough. Let's read the next paper, right? Okay, so let's fast forward, okay? There's this old man living in a hut in Vermont. He's very hard of hearing. No, this is a radio telescope, okay? But again, due to budget cuts, right, they can't build the whole parabola, can they? Yeah, they don't have the whole thing, but you've seen that. Like if you see the movie Contact, they've got that array of telescopes and all this stuff, right? So this is part of a parabola, part of a parabolic dish, yes? And you see these up on the towers, like on the West Hills, when you look at the communication towers. They look like little seashells, right? These are parabolic concentrators. They're receiving, they beam stuff using microwaves and stuff like that for communications purposes. So they'll use big, intense beams for that. This thing is a radio telescope, and this is kind of a funny story, okay? In 1965, they have this thing. These guys are doing something else. They are not trying to discover cosmic microwave background radiation. Now, this telescope has been in existence for, here, David, you want this? This thing has been in existence for I don't know how long, right? Okay? There are scientists waiting in line to use this radio telescope. It's state-of-the-art, real state-of-the-art stuff, right? In fact, these guys have the telescope, and in 2 weeks, about 2 weeks after them, there were some scientists signed up, and they were going to look for the cosmic microwave background radiation. These guys are not looking for it. And they point the telescope in the sky, and they suddenly get this noise. Noise, 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 as like Grinch would say, right? They're pointing it in the sky, and the sky seems full of this crazy hiss, right? And back when televisions were not digital, you could just tune to a station. You see how little snowflakes, yeah? If you still have a television, you can do that. You could watch, tonight, you could watch The Big Bang. Not the movie or the TV series. You could watch The Big Bang, the actual Big Bang. About 30% of those little snowflakey things actually are coming from the Big Bang itself. They're residual radiation from it. These guys were not looking for it. This was actually interfering with what they were doing. They're trying to get rid of it, but they realize that it's everywhere. It's coming from out there, and at first they think it's their equipment, but then they realize it's coming from out there. They publish a paper, they get a Nobel Prize because they've discovered what Gamow predicted 25 years earlier, right? They've actually discovered the first primeval photons from the early universe, right? The two scientists, or a team of scientists that had signed up to use it in 2 weeks are like, dang it. Can you imagine how frustrating that'd be, right? They're like, what is this radiation? Oh, I don't know, it's probably Russians, I have no idea. Okay, it's background radiation. Dang it. Okay. Here is where they discovered it. Now here's the problem, is that they're trying to look at it through the atmosphere of the Earth. Now, the Earth is not neutral. The atmosphere of the Earth is not neutral when it comes to blackbody radiation. It absorbs infrared, it absorbs all sorts of stuff. So the atmosphere itself is something that radiates blackbody radiation. So it's very hard to sit at the bottom of the atmosphere and detect this stuff, right? So the real way to detect it is to spend millions of dollars of taxpayers' money and send a satellite up into Earth orbit above the atmosphere and measure it. Of course, you got to look away from the Earth, away from the sun, right? Okay, and measure the background radiation. Well, This is pretty good.